Jacob, and this is my presentation on the physics of boats.
The earliest civilizations have tended to live near water, so it only seems logical that the people living there would begin to experiment with objects that can float. The history of boats can be traced to 3000 BC, when they were invented in Egypt. The Egyptian boats commonly featured sails and oars and had wooden hulls. The Egyptians, seeking to expand the applications of their invention, created many different varieties of boats to serve a variety of purposes. The warship was designed with speed, adequate space for troops, and maneuverability in mind. On the other hand, cargo ships for trade were designed to be tall and round in shape. The next major innovation in ship design came with the steamboat in the early 19th century. These ships used steam as a working fluid to drive the boat's propellers. Ships have only gotten bigger and faster since then, and now cruise ships are typically powered by diesel engines. Personally, I've ridden and continue to ride on boats of all shapes and sizes. From paddle-powered kayaks and canoes to 1,000-foot cruise liners, I enjoy my time on all boats and ships. Now that you know the history of boats, it's time to look at the intricate scientific processes behind their ability to function. The physics of boats largely has to do with the concept of buoyancy. Buoyancy is an upward force that is exerted on an object that is in a fluid. Archimedes' principle further explains buoyancy, stating that the buoyant force is equal to the weight of displaced liquid by the boat's hull. An object whose density is greater than that of the fluid in which it is submerged tends to sink. If the object is either less dense than the liquid or is shaped appropriately, such as in a boat, the force can keep the object afloat. The density of a boat is equal to the mass of the boat divided by its volume. This is why boats, even though they can weigh many tons, float because they are built to be wide, which increases their volume and lowers density. This idea is shown in the following clip in which marbles are added to a tinfoil boat.
Row, row, row your boat gently down the stream. Merrily, 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 life is but a dream.
Considering the density equation, the marbles add mass to the boat, while the volume remains the same. This means that the density with marbles being added will get increasingly larger since mass is in the numerator, and once the density value surpasses 1 kilogram per meter cubed, which isn't the density of water, the boat will sink. When not in use, the boats are at rest, either tied to the dock or anchored down. This is related to Newton's first law of motion, which states that an object at rest will stay at rest, and an object in motion will stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This can be modeled by free body diagrams, which are diagrams used to show the relative magnitude and direction of all forces acting upon an object in a given situation. As shown in the diagram, the weight of the boat, or the force of gravity on the boat, is pulling in a downward direction. The weight of the boat is equal to the boat's mass times its acceleration. Acting in the opposite direction is a buoyant force, or the upthrust of the water. The buoyant force is equal to the density of the fluid multiplied by the submerged volume times the gravitational acceleration. Since the boat is at rest, this means that the buoyant force and the weight of the boat have the same magnitude, and there is no applied force acting on the boat. In order to get the boat to move, a force must be applied to it, such as through the use of an engine. Since the boat is in contact with the water, there will be a friction force, or drag, that will be applied in the direction opposite to the applied force. The idea of forces is represented in Newton's second law, which states that the force acting on an object is equal to its mass times its acceleration. This is why larger boats require engines that can produce more thrust than for smaller boats. Newton's third law states that for every action, there's an equal and opposite reaction. This is shown when a person jumps out of a small boat, such as a canoe, onto a dock. As a person jumps off, he exerts a force on the boat, and the boat exerts a reaction force on him, which is why the boat will move away from the dock after the man jumps out.
Hi, that was my presentation on the physics of boats, and I hope you learned something, and I hope you enjoyed it.